Good morning, mathematicians. Welcome to day 3 of trying to compute Brauer groups. Sorry. Trying to get to the definition of Brauer groups in Milne's notes on class field theory. This is the third time I've titled this the Brauer group. In anticipation that we might actually reach it. I think today might be the day. We shall see, though. Who knows what silly things I will find myself distracted by. Silly things meaning, of course, comments coming from all of you in chat. It is like Groundhog Day. It's like Groundhog Day for me because you saying that is like Groundhog Day. Someone needs to distract me again. Do they, though? I mean, who better to than the two of you? The most usual suspects. No, I think you guys keep me pretty on track. I believe. I believe in my heart of hearts. Good morning, Ken. That today we'll make it. But I've believed that before and been wrong. Okay. The tensor product of two simple K algebras, at least one of which is central, is again simple. After 117, we may suppose one of the algebras is this, where D is a division algebra with center K. Let A be the second simple K algebra. In the next lemma, we show that this is simple. And therefore, this is isomorphic to this with D prime a division algebra. And so this is isomorphic to this, is isomorphic to that, is isomorphic to that, which is simple. Nice. My job is to distract you. I suppose that's true. I'm just out here making excuses for people to not do their homework. Like, oh, I can't do my homework now. K-theory is streaming about Galois Cohomology. Okay, let A be a K algebra and D be a division algebra with center K. Okay. A is a K algebra, D is a division algebra with center K. Then any two-sided ideal in here is generated as a left D module by the elements belonging to A1. Okay, hang on a second. I don't know why this is just not computing. A is a K algebra. D is a division algebra with center K. Any two-sided ideal in this tensor product is generated as a left D module by this thing. Okay. Really? This makes it a left? Wow, how does this not make it a right D module? Oh, I see. Because it's coming in on the left there. Okay. The ideal of the tensor product is in particular a D submodule. Agreed. We take a basis for A as a K vector space. Then this is a basis for that as a left D vector space. Yes. Oh no, we need to I knew primordial would come up. It just looks so boring and technical. Okay. We might have to go back and read it. So, will we get to Brauer groups? Who knows? If alpha is primordial with respect to this basis, say blah. Okay. For any non-zero delta, this is back in the ideal. And so this is true. Maybe the reason you find all this unintuitive is just because you don't know enough examples of non-field division algebras. Everything's the quaternions, Arad. It's all the quaternions. It's all the quaternions. We love our quaternions. Just meditate on those. Just pretend everything's a quaternion. Let's see. Examples of non-field division algebras. No, we want associativity here. Yeah, quaternions, come on, give us more stuff. What the hell's a cyclic algebra? Boo, it didn't give us anything, didn't give us anything else too interesting, really. Construction of non-cyclic division algebras of degree 4 from Jacobson's book. So we start with a quaternion algebra. Oh, this is just the quaternion algebra. Oh, okay. I don't know. Cyclic algebras are the other thing besides quaternions, but you only know it from Brauer group stuff. I see. Yeah. Whatever, I stand by my comment. Everything's the quaternions. Okay. Where are we here, though, in this proof? In particular... Oh, no, we've got to look at this stuff. This is the set of the non-zero indices or something, right? So, okay, I can believe that those are the same. And so, I guess that there's a lemma that says that that holds in that case. We have to show that every primordial element is in here, which completes a proof, because this is generated by its primordial elements. Ugh. Do we have to go back and read primordial elements? We might have to. Okay, let me just go back. We're not going to do it in detail, because I don't know why. I just look at this statement, and I'm just like... I don't care. A non-zero element is said to be primordial if the set of indices, non-zero indices, is minimal among elements which are non-zero elements of that subspace, and for which in the expression at least one coefficient is 1. Yeah, I'm so confused about this. Why isn't this hello Noel? Why isn't this just always a basis, a single basis element? It would not be that sinful, Arad, but... Well, it's not analysis yet, Noel, but don't worry. We do have L-series and the density of primes coming up in Chapter 6, which at this rate will be a million years before we get there, but don't you worry. This is all heading towards analysis eventually. God, yeah, see, I don't even understand the definition of primordial here. Relative to the basis, I see. So we could have other... Right, it's relative to that basis. So you could be in a subspace and... Right, it wouldn't always be that because that's not a basis of that subspace. Okay, that makes sense. What? And then this is the only proposition we have about it? Right, we had the containment thing, if and only if scalar multiple, and the set of primordial elements of W spans it. Okay. Okay, moving on. And then now this falls out from those results. Okay. Suppose A is a central simple algebra over K, and let V denote A regarded as a K vector space, then multiplication makes A into a left A module. Yes. Wait. Isn't V just what we would have called AA? Central simple algebra V denote A regarded as a K vector space, left multiplication makes V into a left A module. Yeah, why are we calling this V? Weird. And right multiplication makes into a right A module. Or a left A op module. Sure. These actions identify A and A op with commuting subalgebras of and KV. From the universality of the tensor product, we obtain a homomorphism. Right. And so since this is simple, the kernel of the homomorphism and the kernel of the homomorphism does not contain 1, it must be injective. On counting degrees, we find that A tensor with A op over K as an extension of K. Huh? What do you mean? What do you mean by this? What the F does this mean? As a K vector space? I'm weirded out here. You just remembered, isn't there something like Langland's over division algebras because they arise as inner twists of GLN? Yes. That is true. There's like inner forms of one does study like inner forms of GLN, and you look at like GLN over division algebra. Absolutely, that's an important thing. Okay, we're getting so close though. Let's try to stay the course. But what the hell does this mean? On counting degrees? What is the degree of an algebra over a field? What does that mean? I don't understand what that means. I would interpret it to just mean this, like the dimension of the algebra is a K vector space. Yeah. Okay. Whatever. Another Skolem theorem. Okay. Suppose we've got two morphisms. Suppose these are homomorphisms from a K algebra to a K algebra. Are they algebra homomorphisms, I guess? Surely. If A is simple and B is central simple, then there exists an invertible element of B such that this. So that says that all homomorphisms are conjugate to each other. That's flippin' crazy. Then there exists an invertible element B such that this is true. So doesn't that mean then that... Wait, what if F is the zero morphism? Or can we not have the zero morphism because we want 1 to go to 1? Sorry if you're late to the party, but what exactly is Galois cohomology? And does it relate to classical things like the Durham cohomology? Well, you could always go back to episode 1 in the live streams. But in short, I guess the answer is yes. I mean, the question is really, well, what is group cohomology? What is so Galois cohomology is just cohomology really when G is a Galois group, and generally M will be some abelian group that is related to these things. Could be the additive group or the multiplicative group, or it could be the group of units, the group of nth roots, or it could be the group of units of the ring of integers. And these could be like global or local fields or anything. So that's what Galois cohomology is. And so what is group cohomology? Well, I'll let you read up on it or go watch the first episode or first few episodes. But what is... does it relate to Durham cohomology? Well, kind of, because, Durham applies to manifolds, so certainly Durham of a manifold will, certainly agree with, say, the singular cohomology of that topological space. And if I understand correctly, actually historically, the group cohomology, GM, was actually maybe even defined as, or originally came from. So if you have a group G, recall that you can form a space. I forget how we call it, but basically you can we know that there exists a space that's like KNG, where the nth homotopy group of this space is isomorphic to G, and then the rest are trivial. I forget it's Eilenberg-MacLane space or something. And so basically, if I understand correctly, then the singular, you can define this to be the singular cohomology of this space. Maybe this N needs to match or something. Actually, I'm starting to feel like this isn't entirely true, but I think something to this effect is true. There's a fairly common strategy when computing group cohomology of arithmetic groups to model BG as a smooth manifold and exploiting Hodge theory stuff. I would love to understand that eventually. Okay. Why is Skolem nether true? Well, we may as well assume that B is of that form. Wait, is that true? Need we? Whoa, why is this clickable? Open web page? Oh, it's just a weird thing that happened there. It thinks it's a link. I'd love to go to endomorphism.com though. If B is this, then the homomorphisms define actions of A on Kn. Yes. So let these denote the modules with respect to those actions. According to some previous results, two A modules with the same dimension are isomorphic. But an isomorphism is just going to be an element that does this. Nice. Okay. In the general case, we consider the homomorphisms induced here. But because this is a matrix algebra, we can pull that same trick to get this. Nice. If we take A equals 1 in this equation, we find that this is true, and therefore this is in the center, or the centralizer of this thing, which is equal to, I guess using the fact that it's the tensor product of the centers is equal to this thing. But that means this is equal to some B naught. And then taking B prime equal to 1 in the above, we recover this. That is pretty cool. I feel like I should go slower and write it down, but I get the gist of it. Pretty slick. Pretty slick little proof there, right? Well, I'm talking too much. This coffee's like room temperature already. I need to get a coffee maker because apparently filtered coffee filters out some undesirable part of the coffee but retains the polyphenols. So I've heard. Also, I need to get an 88 key keyboard with weighted keys. I feel like I need it now. Anyways, let A be a central simple algebra over K, and B1 and B2 be any K algebras, any isomorphism. Oh, subalgebras. Any isomorphism, which is of those, is induced by an inner automorphism. In other words, there exists an invertible A such that this is true. Because this is a special case of these theorems. That is very interesting. That is very interesting. And this is also interesting, that all automorphisms of a central simple K algebra are inner. Yeah, I guess you just directly apply it to that result. So for example, the automorphism group of n by n matrices is PGL. Wow. Who would have thunk it? And lo and behold, gang, we have made it. We have arrived. It is time. we have broken the cyclic curse that was forced upon us by ourselves. And by ourselves, I mean me. I could end the stream here and not read it. And we could, and tomorrow could also be called Brauer groups. I don't know. I could do it. I have that kind of power, you know. Yeah, okay, let's just read the definition of the Brauer group. Okay. Let A and B be central simple algebras. Wait, really? This is only defined for central simple? No. Really? No, surely it must be more general. We say that A is similar to B if we can tensor up by possibly distinct matrix algebras to get an isomorphism. This is an equivalence relation. It is obviously reflexive and symmetric, and some previous result implies that it is transitive. We define the Brauer group of K to be the set of similarity classes of central simple algebras over K. And we write this for the similarity class, and we get a well-defined associative commutative product on it in this way. Of course, the matrix things are the identity elements, and because this is true, every element has an inverse. There we go. You know, what's interesting is it was my understanding that this has something to do with Morita equivalence. And we do know, for example, that if we have two rings, that Morita equivalence between their module categories, F should be isomorphic as a functor to, well, I think, what is it? It's something like if we take G, no. It's something like tensoring over F applied to A, I think, as an A module. But then this picks up like a B module action here. So maybe just for left-right things, like if these are both left, maybe it's here so that this is a left B module. Yes, this is the way it is. Because this thing, you're plugging in a left A module, and then you can give this, this has a natural right A module structure. So you could take this tensor product. And so it was my understanding that there is also a way to interpret this, and this makes sense with the sort of tensor product definition we saw. It's my understanding that there's a way to interpret this where it gives you like Morita equivalence classes. So I don't know if that's going to be talked about here or not, but maybe I'm misremembering. Okay, Wedderburn's theorem shows that every central simple algebra over K is isomorphic to M and D for some central division algebra D, and that D is uniquely determined by A, even by the similarity class of A, up to isomorphism. Therefore, each similarity class is represented by a central division algebra, and two central division algebras represent the same class if and only if they are isomorphic. Okay. But wait a second. Really? This is only defined for central simple algebras? That's boring. That's boring. I don't care. I don't care about that. Everything we've seen so far has told us that these are extremely boring. We should verify that the similarity classes form a set. Ooh, and not merely a class. Hell yeah, set theoretic issues, baby. Who cares? I mean, we all believe in a hierarchy of growth and deque universes, right? You can define it for Azumaya algebras more generally. Okay. I forget what those are, but I've gone to a talk. I have a friend of mine who used to be at the same university, but then he graduated, and I remember he gave a talk about Azumaya algebras. If we consider these families that are structure constants for central division algebras over K, clearly these families form a set, and each family defines a central division algebra over K. These division algebras contain a set of representatives for the Brauer group. Let's look at some examples. If K is algebraically closed, then this is trivial. To prove this, we have to show that any central division algebra over K equals K. Well, if alpha is in D, and we let K alpha be the subalgebra, K adjoin alpha be the subalgebra of D generated by K and A, then K alpha is a commutative field of finite degree over K. Wait, why is that true? I mean, K is an algebraically closed field, but why is this thing algebraic? I guess it has to satisfy its characteristic polynomial. Alpha is in D. Alpha's in D. It's an element of D. I mean, is there any assumption on D being like finite dimensional? Any central division algebra? Did we have a result saying that it has to be finite dimensional? Yeah, it's not so clear to me. Why does alpha have to be algebraic? Of finite degree over K. Okay, whatever. I'd really like to better understand that. Frobenius showed, hello, Yamin Nu. Ooh, Yamin Nu. Frobenius showed that Hamilton's quaternion algebra is the only central division algebra over R. Therefore, the Brauer group of R is cyclic of order 2, which contains R and the quaternions. Very nice. Wedderburn showed that all finite division algebras are commutative. I remember that result. Therefore, the Brauer group of a finite field is 0. Wait, what? Finite division algebras are commutative. Therefore, the Brauer group of a finite field is 0. Why? Again, wait a second. Is there some finite dimensional assumption somewhere that I'm forgetting about? What if we took some like infinite dimensional thing over a finite field? Um, yeah, is there a finite dimensionality assumption? I don't, I feel uncomfortable. I feel like I'm missing something here. Okay. Hasse showed that the Brauer group of a non-Archimedean local field is canonically isomorphic to Q mod Z, which we're going to see. We're going to see it pretty soon. Oh, what? I didn't mean to do that. Wow, did I just change this in... Did I just change Milne's notes online? CSAs are always assumed to be finite dimensional. Okay. Okay, that explains everything, I guess. Wait, see page 138 below. Yeah, okay. Albert, Brauer, Hasse, and Nether all showed that for a number field, there is an exact sequence. Ooh, very cool. The Brauer group into the Brauer groups of the local fields into Q mod Z. I once heard Brauer. Oh, we got a first-hand account. Who normally had a gentle manner, deliver a tirade against modern mathematicians who ignored the distinction between sets and classes. As he pointed out, if you ignored the distinction, then you obtain a contradiction. And once you have a contradiction in your system, you can prove anything. Yeah, I guess. I mean, about 2 years ago, I had a very serious existential crisis about the fact that everyone was flippantly assuming the existence of growth and deque universes without even knowing it. But now I don't care. Very cool. Okay. I guess next time we will talk about extensions of the base group. Base field. We finally did it, gang. We made it to Brauer groups. How much further will we go before we take a break? I don't know. I do want to go a little bit further with Brauer groups. But that's it. That's all. So yeah, go prove some stuff about